Good day, grade 12 learners and teachers. Welcome to today's mathematics lesson. My name is Sibusiso Shongwe, and this lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Right, today we are looking at the last subtopic for the year or for grade 12. That is part of probability and counting. We are zooming into the fundamental counting principle. It's regarded as one of the most difficult topic for learners, but we want to change the narrative this year because mostly you guys don't attempt questions in counting principle. So we want to change that narrative this year and make sure that you respond to the questions in the counting principle. We'll try to break it up into small pieces, which when combined will form a whole. Right, we are looking into the lesson objectives for today. By the end of this lesson, you'll be able to, or you should be able to understand the origin of the counting principle, understand the factorial notation, use counting principle to arrange objects without repetition, use counting principle to work with seating arrangements, use counting principle to work with book arrangements, use counting principle to also work with word arrangements. We will next week look at digit codes and arranging rest of the object as well as application to probability problems. Now, you can refer to CAP's document on page 49 as well as the examination guideline on page 7 to see what is actually wanted from you or what is expected from you as far as probability and counting is concerned. Right, you should bring the following knowledge to this lesson: the terminology that you dealt with in probability, complementary events, mutual exclusive events and inclusive events, independent and dependent events, as well as exhaustive events. You should also know the probability equation as well as probability identities. Right, let's begin with our background. We all know that from elementary stages, we know that mathematics began with counting. Usually we used our fingers to count 1, 2, 3, 4, and so on. We also used some cold drink lids to perform some operations. For an example, addition, you take 3 cold drink lids and take 2, and then you combine them, and then when you count the total, you find that it's 5. That's how we began our counting. Now, but what happens when we want to count large number of items? This chapter will then focus on how we can use mathematical technique to deal with different assortments of items. Right, an important aspect to probability theory is the ability to determine the total number of possible outcomes when multiple events are considered. Now let's look at the following 2 events. Suppose that you have 3 t-shirts and 2 trousers. How many different outfits can you wear? You have 3 t-shirts and 2 trousers, and you want to know how many different outfits you can wear. And we are instructed here to use a tree diagram. Now, in using our tree diagram, let us say we begin with the t-shirts. The options that we have for the t-shirts: we can wear t-shirt 1, we can wear t-shirt 2, we can wear t-shirt 3. Let me call the t-shirt S, shirt 2, as well as shirt 3. Those are the 3 t-shirts. Remember, you will wear those t-shirts with trousers. So if you've decided to wear t-shirt 1, then there are 2 possibilities as well for trousers. You can wear t-shirt 1 with trouser 1, or you can wear t-shirt 1 with trouser 2. However, if you decide to wear t-shirt number 2, you can wear t-shirt 2 with trouser 1. You can wear t-shirt 2 with trouser 2 as well. However, if you decided to wear t-shirt 3, you can wear that with trouser 1, or you can wear that with trouser 2. That is how we represent that in our tree diagram. But obviously we know our tree diagram will have outcomes. The first outcome here would be you can wear t-shirt 1 with trouser 1, or you can wear t-shirt 1 with trouser 2. As we go on with this, we see that we can wear t-shirt 2 with trouser 1 or t-shirt 2 with trouser 2. Moving on, we can wear t-shirt 3 with trouser 1 or t-shirt 3 with trouser 2. Now, if you check here, these are the outfits that we have. We have the first outfit, the second one, the third, the fourth, the fifth, and the sixth. So we have 6 different outfits. We have 6 different outfits when we make use of our tree diagram. You can see that it can be t-shirt 1 and trouser 1, or t-shirt 2 and trouser 2, t-shirt 2 and trouser 1, t-shirt 2 and trouser 2, t-shirt 3 and trouser 1, t-shirt 3 and trouser 2. So those are 6 different outfits that one can wear. Now, moving right along. Now, what if we were given 500 t-shirts and 200 trousers? Now, you see that it would not be practical for us to draw our tree diagram to try and find the number of outfits that we can wear. It would be a very tedious task to try to attempt that using a tree diagram. That is why now we introduce rule 1, the fundamental counting principle. Rule 1 states that if there are m ways of performing one task and n ways of performing another task, then there will be m times n ways of doing both the tasks. So if you have m ways of doing one task and n ways of doing the other task, to do both of them combined, you'd have m times n ways. Now, we can revisit example 1 using rule 1. Now, if you check, we have m is equals to 3 t-shirts in this case, and we have n is equals to 2 trousers. That is what we had in example 1. And according to the fundamental counting principle, the total number of outfits would be given by m times n. That is what the fundamental counting principle states, which means that this would be 3 times 2. This gives us 6 possible outfits. It gives us 6 possible outfits. It's the same as what we got when we used our tree diagram. But now in this one, we are making use of the fundamental counting principle. Right, moving right along. Example 2, we now want to determine the number of ways a netball team consisting of 7 players can arrange themselves in a line for a group picture. How many ways can 7 players arrange themselves in a line to take a group picture? Now, learners, here you need to be very, very careful when dealing with aspects of the counting principle. The counting principle is concerned with the number of options that you have. You are not specifically making a decision, but you are asking yourself, how many options do I have of coming up with that particular decision? How many options do I have of making a specific decision? You are not actually making the decision per se, but you are asking yourself the total number of options that are available to make that particular decision. That's very, very important. Right, now we have 7 players, they want to take a group picture. We want to know how many ways they can arrange themselves. Now, because you have 7 players, we can open 7 positions. 4, 5, 6, 7. Now we've opened 7 positions for all the 7 players, and then we are going to fill these positions from left to right and see how best we can do that. Now, the first thing that we're going to do is, when filling the first position, we're going to ask ourselves, how many options do I have of filling that position? How many choices do I have? Now, if you have 7 players and all of them, obviously, they have different names that you can use, you can put any of them in the first position. So we're going to say that we have 7 options because all of them have equal chances of being in the first position. So here you're going to have 7 options of filling the first position. It's 7 options of filling the first position. Now, when we move on to the second position, we ask ourselves, how many options do I now have? Now, learners, you see that you've already used 1 option. If you check for the first position, I wrote 7. The 7 does not mean that I will put all 7 of my players in that position, but it specifically means I have 7 options of filling that position. Obviously, it's only one learner who's going to fill that position, or one player who's going to fill that position. Once that position is filled by that one player, we ask ourselves, for the second position, how many players or how many options are available? It should be 6 options, because already the first position has been occupied by the first player. Now, for the third position, you've now used 2 players and 2 positions. Now you fill in the third position, that would be 5. The fourth position, that would be 4. The fifth position, 3, and then 2, and then 1. So those are the options that are available for you. So therefore, the total arrangement in this case would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Because remember what the fundamental counting principle states. It states that if you have m ways of doing one task and n ways of doing the other, then you have to multiply those options combined. Right now, we need to check what 7 times 6 times 5 times 4 times 3, 2, and 1 would be. It would be 50, 40. So that is the total number of arrangements that you can have, because the players can interchange positions to take that picture. So you'll have 5,040 ways in which they can take that picture. Right, moving right along, we move on to example 3. We have a school plays a series of 4 soccer matches, and for each match there are 3 possibilities: a win, a draw, or a loss. So they play 4 matches, and we know for each match there are 3 possibilities. It's either a win, a loss, or a draw. How many possible results are there for the series? Remember, the series consists of 4 soccer matches, so we're going to open 4 spaces: 1, 2, 3, 4. And then we ask ourselves, for the first match, obviously this position represents now the first match. This position represents the second one, this one the third, and this one the fourth. Now, we are interested in finding the number of options that I have of occupying the first position or the first match. How many options do I have? Obviously, we said we had 3 possibilities: a win, a loss, or a draw. So for the first match, there can be a win, a loss, or a draw. Now, after playing the first match, you go to the second match. For the second match as well, there can be a win, a loss, or a draw. Remember, the results of the second match are totally independent of the results of the first match. You can win both matches, you can lose both matches, or you can draw both matches. The results of the first match are totally independent of the result of the second match. The third match, there are 3 possibilities. Fourth match, 3 possibilities as well. And according to the fundamental counting principle, if we have 3 ways of performing task 1, 3 of performing task 2, 3, and 4, then we have to multiply all those options combined. Therefore, we have that the total result in this case would be 3 times 3 times 3 times 3, which will then become 3 exponent 4, which gives us 81. So we have 81 possible result for this particular series. Right, we move on. Example 4. A young man takes his girlfriend out for dinner at a restaurant. The following menu is available. Now we see for drinks, we have Coke, orange juice, coffee, and tea. And then we have the main course, and we have options for the main course as well as the dessert. We have options for the dessert as well. His girlfriend decides, all right, let's go back. The first question, there's an error here. The first question was supposed to be how many different meals can you have? How many different combinations of meals can we have? This question is supposed to be question number 2. So the first question should be about the total number of meals. Meal combination. How many different meal combinations can we have? Now, we are going to say now total combination, total meal combinations. We have obviously drinks, we have the main course, and we have drinks here, we have the main course, and we have dessert. Now for drinks, we have 4 options. For the main course, we have 5 options. And for dessert, we have 3 options. Now, in order for us to have all these combined, we're going to use the fundamental counting principle and multiply. So that would be 4 times 5 times 3. When we multiply the 3, we get that this is 60 combinations. That will give us a total of 60 meal combinations. Remember, I said there is a mistake with this question. This is the second question. The first question asks about the total number of meal combinations. It's the total number of meal combinations. Right, moving right along. The second question, his girlfriend decides to have a beef wrap with chips as her main course. So the girlfriend has made a decision for the main course. She decides to have beef wrap with chips. She decides to have this beef wrap with chips as her main course. How many different meal combinations can she now choose? Now we go back, we say total number of combinations would be given by, we have drinks, we have the main course, and we have dessert. Now, how many options do we have for drinks? It's obviously 1, 2, 3, 4. She can choose from any of those 4 options. So she has 4 choices for drinks. How many choices does she have for the main course? For the main course, she has made a decision that she wants to have beef wrap with chips. So there is only 1 option there. It's no longer 5 options like the previous question. It's 1 option because she has made a decision that she wants to have beef wrap with chips. For dessert, there are still 3 options available. So the total combinations would be 12. So the total number of combinations in this case would simplify to 12 when she decides to have a beef wrap with chips as her main course. Right, moving right along, we now define a unique way of performing some calculations or a unique way of counting in maths, which is called the factorial notation. There is a unique way to write some of the calculations that we've already seen, like for an example, in example 2, where we had 7 netball players, where the calculation involves multiplying numbers that are reduced successively by 1 till we get to the number 1. If you still remember, the total arrangement that we had in example 2 was 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, if you check these numbers, we are multiplying numbers that are reduced successively by 1. So we are decreasing the numbers by 1 up until we get to the number 1. And this notation is called the factorial notation and denoted by the mathematical symbol. Good people, this is a mathematical symbol. It's not the same as the exclamation mark that you use in language. It's not the same. This is a mathematical symbol that is used to count numbers that are reduced successively by 1 until we get to the number 1. Now, generally, we use n factorial as n. If you check, it's n. And then we subtract 1 from n, we get n minus 1. We subtract 1 from n minus 1, we get n minus 2. We subtract 1 from n minus 2, we get n minus 3. We go down up until we get to 3, 2, and 1. That's where our counting stops. And by definition, 0 factorial is equals to 1. 0 factorial is equals to 1. Now, the first question asks of us to determine 5 factorial. So to determine 5 factorial, what we're going to do is we're going to say 5 factorial is equals to 5 times 4 times 3 times 2 times 1. If you multiply that, you're going to get that this is 120. Now, in your calculators, there is a factorial button. The factorial button is there. It is there. In most calculators, it's represented by the second function or the shift, but the factorial button is there and can be used. Now, if you check the second one, they say determine 8 factorial over 4 factorial. Now, there's something I want to show you. If you look at 5 factorial, we said it's 5 times 4 times 3 times 2 times 1. If we can look at 4 times 3 times 2 times 1, this is the same as what? 4 factorial. So our 5 factorial is the same as 5 times 4 factorial. This is also the same as, remember, if you have 4 times 3 times 2 times 1, if you can just start from 3, 3, 2, and 1 is the same as 3 factorial. Which means if you have, say, 10 factorial, you can write it as 10 times 9 times 8 times 7 times 6. That is 10 times 9 factorial. If you like, you can write it as 10 times 9 times 8 factorial. Because remember, as you reduce successively until you get to the number 1, you say you have a factorial. We can use another example. Let's take, for an example, 6 factorial. We know 6 can be written as 6 times 5 times 4 times 3 times 2 times 1. That is 6 factorial. If we want to cut it at 3 for argument's sake, we can write this as 6 times 5 times 4, but 3, 2, and 1 can be written as 3 factorial. Right. 11 factorial can also be written as 11 times 10 factorial. That's how you deal with these factorials. Now, let's look at example 2. It says, show that 8 factorial over 4 factorial is 8 times 7 times 6 times 5. Now, if we break this up, 8 factorial over 4 factorial. 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That is 8 factorial. What about 4 factorial? Is 4 times 3 times 2 times 1. So this whole part here and this whole part in the denominator are going to divide out. You'll be left with 8 times 7 times 6 times 5, which is what they actually wanted you to prove. which is the same as what we have on that particular problem there. Alternatively, it's the same as what we had on the right hand side. Alternatively, we can do it this way. Can have another way of doing it. Alternatively, we can say 8 factorial over 4 factorial is the same as 8 times 7 times 6 times 5 times, it will be 4321. And 4321 is the same as 4 factorial. Divide by 4 factorial. So the 4 factorial and the 4 factorial will divide out. You'll be left with 8 times 7 times 6 times 5. That's basically what we are working with. Right, moving right along. Now that we've defined our factorial, we can then move on to rule 2. Rule 2 states that the number of arrangements of n different things taken n different ways is n factorial. Say for an example, you have 5 books that you want to arrange in a shelf that has 5 spaces, then you can arrange them in 5 factorial ways. They are saying it's n different things taken n different ways. You have 5 books, you want to arrange all 5 of them. Then you can say that is given by n factorial or 5 factorial. Now, the first question, or example 6, asks of us to calculate or determine the number of ways we can arrange 5 different books in a shelf. Right, this is the total arrangement. Obviously, it's 5 books. We can open 5 spaces, 2, 3, 4, 5. For the first position, we have 5 options. For the second position, we have 4 options. For the third position, we have 3 options. For the fourth position, we have 2 options, and then we have 1 option. That is, if we multiply them together, we're going to get 120 ways. 120 ways. Alternatively, or by using rule 2. By using rule 2, the total arrangements will simplify to. Since we have n different, 5 different books, and we want to arrange all 5, that would be given by 5 factorial. And if you put 5 factorial in your calculator, you're going to get that it is equals to 120 ways. It is exactly equals to 120 ways. Right, moving right along with this, we move on to rule number 3. Remember, rule 1 was talking to the fundamental counting principle. If you have m ways of performing one task and n ways of performing another, then to perform both of them combined, you'd have m times n. That was rule 1, the fundamental counting principle, or the basis of all the rules that we're going to use. And then rule 2 says if you have n different objects and you want to arrange n of them, then you can do that in n factorial ways. Now we move on to rule 3. Rule 3 says if you have n objects and you want to arrange r at a time, then that's given by n factorial over n minus r factorial, or NPR. We call this the permutation. We call this the permutation. The permutation is used to work out or to calculate the arrangement of objects. If you have n different objects and you want to arrange less than n of them, then you can do that using the permutation. The permutation button is also in your calculators. In your calculators, it's usually denoted NPR. So you will start by putting the number n, and then you'll press the permutation button, and then you'll put the number r, and then you'll be able to find that specific answer of that specific arrangement. Right. Now, let me explain again rule 3. Rule 3, let's say you have 5 books, but now you no longer want to arrange all 5. You want to say maybe arrange 3 of them. Because you want to arrange less than 5 of them, we can make use of a permutation in this case. All right, we have 9 different books. How many ways can we arrange 4 of them? Now, if you check here, the total number of books is 9, but we want to only arrange 4 of them. So we're going to make use of our rule number 3. Alternatively, we can also use the fundamental counting principle. Right, let us revert to the first method. Method 1, let us use method A. We're going to use rule 1. Let us use rule 1, the fundamental counting principle. I have 9 books. I want to arrange only 4. So the total arrangement would be, I want to arrange 4. 1, 2, 3, 4. Because I want to arrange only 4 of them, I'm going to ask myself, how many options do I have of placing the first book in the first position? Since I have 9 books, I'll have 9 options for the first position. And then I'll have 8 options for the second position. Why is it 8? Because I've already used 1 book. I've already used 1 book, so I'll have 1 less book to use, or I'll have 1 less option from the overall number of options. Now the third one, I've used now the second book, so which means that I'll be left with 7 options, and then the fourth one, I'll obviously be left with 6 options. Now if you multiply that, 9 times 8 times 7 times 6 using your calculators, you get that this is 24 ways. 24 ways. Right. Now, we can also make use of method B, that is rule 3. We can make use of the permutation. We can make use of the permutation. Right. If you make use of the permutation, N represents the total number of objects and R represent the number of objects that you want to arrange. So you have 9 books and you want to arrange only 4 of them. So this would be 9 permute 4. That would be the total arrangement. It would be 9 permute 4. And if you put that in your calculator, you start with 9 and then you go to the permutation button and then you permute that 4 ways, and then you're going to get that as 24. It's the same set of solution, right? Alternatively, if you look at this, we can also make use of this. Permutation, by definition, means you will take the 9 at the top, that is 9 factorial, over, and then you can divide that by the difference between the top and the bottom, so that would be 9 minus 4 factorial. Now, if you check this out, this would be 9 factorial over, this would be 9 minus 4, that's 5 factorial. Now, if you check 9 factorial is 9 times 8 times 7 times 6 times 5 factorial, because it will be 5, 4, 3, 2, 1 times 5 factorial. This is divided by 5 factorial. Now, if you divide this and that, you get that this is 9 times 8 times 7 times 6, which is exactly the same as what we got there. So irrespective of the method that you use, whether you make use of rule 1 or you make use of rule 3, you get to the same set of solution there. So which means that one needs to understand the fundamental counting principle, and one needs to understand how these rules work for one to be able to solve this specific questions. Now, with the counting principle, we learn through doing. So the more of these arrangements that you make, and make a lot of mistakes, you get to understand how to specifically do those arrangements. Right now, we have activity 1 for you to do. I'll give you 3 minutes to do that. Please make sure that you finish that in 3 minutes so that we can be able to move to our solution. And remember, we have our WhatsApp interactive number. It should be at the bottom of your screen, but if it's not there, it is 064-748-8913. You can use that number to ask questions and to interact with us. Right, your 3 minutes start now. Hello and welcome back. Right, I gave you a problem to look at. It's the first activity for today. It says 6 swimmers are hoping to take part in a race, but the pool has 4 lanes. In how many ways can 4 of the 6 swimmers be assigned to the lanes? Right, if you look at this problem, we have 6 swimmers and the pool has only 4 lanes. So we can only arrange 4 of the 6 swimmers, not all of them. Remember, if it was all of them, it takes us to rule number 2, but because we want to arrange less, it takes us to rule number 3, which we can make use of or can solve by making use of a permutation. Right, now we're going to start with the first method. We use our first method, that is method A. We have the total arrangement that we are interested in here. We have 6 swimmers. They want to take a part in a race. The pool has 4 lanes, so we have 1, 2, 3, 4 lanes, and then from there we want to know how many ways can we arrange 4 of these 6 swimmers. Now, if we look at the first position, now we ask ourselves the number of options that we have. Since we have 6 swimmers, all 6 of them have equal chances of occupying the first position. So we have 6 options here. And then for the second position, now that the first position has been occupied by 1 swimmer, remember we had 6 options, but the position is only going to be occupied by 1 swimmer. That's very, very important, grade 12s. We have 6 options, but that position is going to be occupied by only 1 swimmer. Now that 1 swimmer has occupied that position, we move on to the second position. Now, in the second position, we have 1 less swimmer now, which means that we have 5 options of occupying the second position. However, that position is going to be occupied by 1 swimmer. But remember, the counting principle asks or is concerned about the number of options that we have. Now, for the third position, we are going to have 1 less swimmer as well, 4, as well as then 3. Now, if you multiply 6 times 5 times 4 times 3, 5 times 4 times 3, using our calculators, we get that it's 360 ways. It's 360 ways. Alternatively, if we make use of method B speaks to rule number 2, where we can use the permutation. So the total arrangement would be, we have 6 swimmers, we only want to arrange 4 of them. So that is 6 permute 4. Now, to do that, we can obviously go to our calculators. We start with 6, and then we press our permutation button, and then we press 4. And then we get that this is 360 ways as well. Obviously, we can also make use of the same rule, rule 2, which will then now tap into the definition of a permutation. It will say, if you have a permutation, you'll take this number at the top, the 6, that is 6 factorial, over, you subtract the top number from the bottom one, that would be 6 minus 4 factorial. This would be the same as 6 factorial over 2 factorial, and then you'll get that that's as 360 ways. That would be 360 ways. Right, moving right along, grade 12. Arrangement of object with constraints or restrictions. Now we are starting to dive into the counting principle. We are going to look into restrictions now. It's very, very important for you to listen and understand what we are going to be doing. The procedures here are not that complex, but you need to listen so that you can be able to apply those procedures. Now, in counting problems, we often encounter arrangements where there are certain restrictions which must be adhered to. These restrictions may include restrictions on certain positions or requirement for a certain object to be grouped together. Now, if you have such problems, we need to take note of the following. If the objects are grouped together, treat those objects as a single item that can be moved within an arrangement. If you are grouping, you treat the whole group as a single item which can be moved within an arrangement. If the position of the object is specified, if you are told this person must be in the first position or must be on the left-hand side, then you need to fix the position of that particular person so that that person cannot be moved within the arrangement, because we are certain that that particular person should be on the left-hand side of a particular arrangement. Now, if objects are grouped together and the position is specified, we treat the group as a single item and we fix its position. But remember that within the group, there can be arrangement depending on the demands of the question. Right, let us see all these guidelines applied in problem solving. Right, we are on example number 8. We are on example number 8. In how many ways can 6 boys of different ages be seated in a bench if they sit in any order? If they sit in any order. We have 6 boys. If they sit in any order, remember it's 6 boys of 6 different ages and we want to align all of them. We don't want to align less. We want to arrange all of them. So we go back to rule 1. Rule 1 says the total arrangement would be 6 factorial. The total arrangement would be 6 factorial. Obviously, one can also make use of the dash and the number method to say the total arrangement would be, you have 6 boys, you can open 6 spaces, 3, 4, 5, 6, and then you say for the first position we have 6 options, for the second 5, for the third 4, 3, 2, and 1, and then you multiply all those together. That is if you use the dash and the number method, that is more consistent, or that is more reliable in the fundamental counting principle. However, we can see it's 6 boys and we want to arrange all 6, so we make use of rule 1, that is 6 factorial, and we check 6 factorial in the calculator. We get that this is 720. That is 720 ways. That is the first one. Now, the second one, the youngest boy sits next to the oldest boy. Now, you see, now there's a condition. We call it in counting principle a constraint, or we call it a restriction. So there's a certain condition now. Now we want to deal with that condition. It says the youngest boy sits next to the oldest. Now what we're going to do is we're going to then group them, the youngest and the oldest, which means when they move within that particular arrangement, they should be moving together. That's what it says. The youngest boy sits next to the oldest boy, which means as you move them within the arrangement in the bench, they should move as an item. That is why we say when we have a group, we treat that group as a single object. So we treat this as a single object, one object, because they now move together as a group. Now, if the youngest sits next to the oldest, how many are left to arrange? How many boys are left? Youngest and oldest, that accounts for 2 individuals, and we have 6 boys in total. So we have that 4 boys remain. 4 boys remain. Now, if our 4 boys remain in this case, and we want to make this arrangement, it means that now we are arranging the 4 remaining boys plus the youngest and the oldest as an item, because they move as a single group, which can interchange positions within that specific arrangement. So now it means that we have 5 objects to arrange, because it's the 4 remaining boys plus the 1 object from the youngest and the oldest, because they always move as a unit. So if we have 5 objects to arrange, using rule 1, we can arrange them in 5 factorial ways. If we make use of rule 2, we can arrange these 5 objects in 5 factorial ways. Right? That's the first thing that we need to consider. Now, when we zoom into the youngest and the oldest, we can see that we can start with the youngest, then the oldest. Or we can start with the oldest, then the youngest. You see, within the group, there can be an arrangement. Within this specific group, there can be an arrangement. The youngest and the oldest can interchange positions. In how many ways can they do that? They can do that in 2 factorial ways. So the total number of arrangements would be 5 factorial times 2 factorial. This gives us a total of 240 ways. It gives us a total of 240 ways. Right, moving right along. But before we move on, let us just recap on what we did on this problem. They said the youngest must sit next to the oldest. So you treat the youngest and the oldest as a single object. If you treat them as a single object, then you can then move that object within the arrangement because there are 4 boys remaining. You can interchange the position of these 2 as a group together with this 4, which means you now have 5 objects to arrange, which can be done in 5 factorial ways. But within them, if this is the youngest and this is the oldest, they can also interchange positions. They can also interchange positions, which can be done in 2 factorial ways. Right, moving right along, the youngest boy sits at the beginning of the bench and the oldest boy sits at the end of the bench. That is another restriction. The youngest sits at the beginning of the bench and the oldest sits at the end of the bench. So this would be occupied by the youngest. You need to fix the position of the youngest because he should be in the beginning of the bench, and we need to fix the position of the oldest here. He should be at the end of that particular bench. So we're fixing those respective positions because we want the youngest to be in the beginning of the bench and the oldest to be at the end of the bench. Now, how many boys are left? Out of the 6, we've placed the youngest and we've placed the oldest. So it's 4 boys remain. Now, these 4 boys that are remaining, obviously, the first position and the last positions have been occupied. You can no longer arrange. You can't arrange for the first and last position, which means that if you fix those positions, they cannot move within the arrangement. They are there on the first position and last position. So the only thing that you can move are the boys remaining. Those that are remaining are the only ones that can be arranged. So how many options do we have for the oldest? We have, for the youngest, it's 1 option. And then for the oldest, it's also 1 option because there's 1 oldest boy and there's 1 youngest boy. So the total arrangement in this case would be 1 times. The 4 boys that are remaining can interchange positions. They can do that in 4 factorial ways, and then the oldest can sit in the last position. So it's 1 times 4 factorial times 1. So we get that this would simplify to 24. So there would be 24 ways. There would be 24 ways. Now we're starting to look at constraints as well as restrictions. That's how you basically deal with them. Right, let us move on and see. Now I have an activity for you to do. I'll give you 4 minutes to do that. I'll give you 4 minutes to work on this activity. Try to arrange these 4 girls and 5 boys in a row. You have 4 minutes to do that, and your time starts now. Right, welcome back. We are on the second activity that you guys need to do. Remember, you can interact with us on our WhatsApp number, which is on your screen just below. If it's not there, you have that as 064-748-8913. Please interact with us. Any questions that you might have from the previous examples that I've done with you, you can pose those questions. We can interact with you via that WhatsApp number. Right, let's move on to this activity. Calculate the number of ways we can arrange 4 girls and 5 boys in a row so that they sit in any order. Now, if you check here, it's 4 and 5, so that is 9 individuals in this case that we have to arrange. Now, if they sit in any order, you have 9 individuals. You want to arrange them in any order, so we can do that in 9 factorial ways. Obviously, you can use that the reliable number dash and number method. If you put that in a calculator, you get 362,880 ways. Now, you can obviously open 9 spaces and start filling those spaces with those options. You are also allowed to do that. That is by making use of the fundamental counting principle. That is rule number 1. Right, now the girls sit together as a group and the boys sit together as a group. So we have this constraint now. The boys sit together as a group and the girls sit together as a group. Now, if we want to arrange those ones, the girls sit together, we can have our girls as a group. There are 4, so it will be our girl 1, girl 2, girl 3, and girl number 4, because they sit in a group. The boys do the same. 5 of them, 1, 2, 3, 4, and 5. It's boy 1, boy 2, boy 3, boy 4, and boy number 5. So they sit together as a group as well, which means that when you move the girls, they have to move as a unit. When you move the boys, they have to move as a unit. So in this case, we said we treat the group as a single object. We have one object here. We have another one object there. So now if you check, we have 2 objects because we have 2 groups that can interchange position. The girls can be on the left and the boys on the right, or the boys can be on the left and the girls on the right. So you have 2 groups to arrange. So in arranging them, the total arrangement should be 2 factorial. This 2 factorial is for the group. It's for the group. 1 group for girls, 1 group for boys. Now, but if you are to continue with this, you will see that there are 4 girls. Girl 1, girl 2, girl 3, and 4. They can also interchange positions. Girl 2 can be the first one, or girl 3, or girl 4. So they can interchange positions among themselves. That is within the group of girls. We can have different positions. They can interchange positions. Since they are 4, they can do that in 4 factorial ways. Now, if you zoom into the boys as well, there are 5. They can interchange position. Any one of them can sit anywhere with respect to the group. But since there are 5, that can be done in 5 factorial ways. So this 4 factorial is for the arrangement of girls, and this 5 factorial is for the arrangement of boys, because they can interchange positions. Now, if you multiply that, you get 2 factorial times 4 factorial times 5 factorial. Now, that simplifies to 5760 ways. That is 5760 ways. That is for B. That is for question number B. That is 5760 ways. Now, the last one, 1 boy and 1 girl are a couple and they want to sit next to each other at any end. So these 2 want to sit next to each other. Now, if you look at this, if you are to look at it on a practical perspective, you have a couple. These two are a couple and they want to sit at any end, which means they can sit at the beginning of the bench or they can sit at the end of the bench. So we have two possibilities. They can sit at the beginning of the row or they can sit at the end of the row, which means we have two possibilities for them to sit at any end. So we can talk to the beginning of the row, beginning of row. If they sit at the beginning of the row, we have that this would be the couple, boy and girl. Let's use one for argument's sake. Boy one and girl one are a couple. They want to sit at the beginning. So we need to fix their position because their position is specified. They sit at the end. In this case, we said beginning of the row. Now, because we've aligned them, how many individuals are left to arrange? We've used, out of 9, we've used 2, which means that 7 people to arrange. We are left with 7 people to arrange. Obviously, these 2 cannot be arranged because they are already placed at the beginning. So we need to arrange the 7 remaining boys or the 7 remaining people or individuals here. So it would be the total arrangement, the first total arrangement for the beginning. The total arrangement for the beginning would be, obviously, it's 7 people to arrange. I can do that in 7 factorial ways. And then the boy and the girl, which are a couple, can also interchange positions. I can start with, in this case, I started with a boy. I can start with a girl, so they can interchange positions. So that can be done in 2 factorial ways. So that is the beginning, the arrangement at the beginning. So we can also have the arrangement at the end of the row. If they are at the end of the row, then there they are. Boy 1 as well as girl 1. They are at the end of the row. If they are at the end of the row, obviously it's 7 people that are left to arrange. 7 people to arrange. 7 people to arrange. So if we arrange these 7 people, we can do that total arrangement at the end of the row. It would be equals to, it would be 7 factorial for the 7 remaining individuals. Multiply by, in our couple, they can interchange positions. I can start with a girl or a boy. So this would be 2 factorial ways. Therefore, allow me to finish this up at the top there. Therefore, the total arrangement in this case would be given by, it should be 7 factorial times 2 factorial plus, we unify that, 7 factorial times 2 factorial. We are now using our probability union because we have this occurring here or occurring there. So we need to take the union of those particular combinations. So we would have that this is 7 factorial times 2 factorial plus 7 factorial times 2 factorial. This simplifies to 20160 ways. That is what we have, because we have 2 options here of them sitting at any end. They can sit at the beginning of the row or they can sit at the end of the row. So we isolated those options, those 2 options, into 2 cases. Case 1, beginning of the row. Case 2, end of the row. Then we unify them to get the total number of ways. So that is how we're supposed to work with this activity number 2. Right, we move on. We get to book arrangements. Now we are arranging books. We no longer dealing with seating arrangement. Now we are dealing with book arrangement. Now, if you check here, I've highlighted the word different. You'll see on the lesson next week, this word different will change to identical. And when it changes, the mathematics that is used there also changes. But you need to log in next week so that we can look at such problems. But for now, we are looking at the different mathematics books and the different physical sciences books. So with mathematics, we have 4 books, and then with the physical sciences, we have 6 books, which means that we have 10 different books to arrange. Remember, for the mathematics, you can have an algebra book, function book, sequences book, geometry book, trigonometry book. So they are different. With physical science, you can have your Newton's laws book, you have your electrostatics books, you can have your organic chemistry book, you can have your rate of reaction books, and so on. So they are different, and you want to arrange them, and if they stand in any order, they are 10 books. If they stand in any order, the total arrangement would be 10 factorial because they stand in any order. So that takes us to rule number 2. So that is 10 factorial. If we make use of 10 factorial, we put it in the calculator, we get 3628800 ways. So these are the total number of ways in which they can arrange themselves there. Now, the second question, the books in each particular subject must stand together. The books in each particular subject must stand together. Now, this one, they want the maths books to stand on their own. They want the physical science books to stand on their own. And they want to know the total number of arrangements. So what we can do is we can just simplify this and group them. We have 4 different maths books: maths 1, maths 2, maths 3, and maths 4. They should stand together. And then you have the physical science books: physical science 1, 2, 3, P3, P4, P5, and P6. These are the physical science books. So because they must stand together, you treat these ones as one object. And then you treat these ones as well as one object. Now if you check, because they are grouped together, you can arrange group 1 and group 2. You start with group 1, then group 2, or you can start with group 2, then group 1. So there is an arrangement of the groups of books. So we can have that our total arrangement, since we have 2 groups, it would be 2 factorial ways. The 2 factorial, obviously this is for the groups. The 2 factorial is for the groups. But now if you zoom into the mathematics books, since they are 4, they can also interchange positions. You can start with M4, M2, M1. You can interchange the respective positions of the books. Since they are 4, then they can interchange in 4 factorial ways. This is for the mathematics. That's for the maths. And then if you look at the physical science books, they can also interchange those respective positions. In how many ways can they do that? Since there are 6, they can do that in 6 factorial ways. That is for the physical sciences. That would be for the physical sciences. Now, if you look at, you work this out in your calculator, 2 factorial times 4 factorial times 6 factorial, this gives us 3, 4, 5, 6, 0 ways. So these are the number of ways in which these books can be arranged if a book of each particular subject stand together. Right, we move on. Oh, I'm already done with this. It's the continuation of example 9. If you check, I squeezed all the solutions in that particular slide. So this won't work. Now activity 3. Remember what I said when we started. I said in counting principle, we learn by doing. We should make a lot of mistakes so that we can learn and minimize the mistakes that we can make in an examination. So now I have activity 3 for you to do, and I want you to do that in 4 minutes. In 4 minutes, you should be done with all the 3 problems, and your time starts now. Hello and welcome back. Right, I hope that you are done with example with activity 3. Let us look at it together and see how you are supposed to work out those solutions. Right, we have 3 different economics books, 4 different accounting books. It's 3 different economics, 4 different accounting, and 6 different business studies books. Now we are on the commerce books. Nice. To be arranged in a shelf. How many ways can you arrange them if the books can sit in any order? So that is the first one. They can sit in any order. The total arrangement, since we have 4 plus 3, it's 3 plus 4 plus 6. That would be 13 books to arrange. So this one here would be 13 factorial. So if we put 13 factorial in our calculators, we get that this is 62270 20800 ways. Right, that's the first one. That's the first one without any restrictions. Now, if you look at the second one now, there are restrictions. They are actually asking us to group books in each particular subject together. So they need to stand together. So we'll start with our economics books. It's economics 1. Let me write it down here. It's economics 1, economics 2, and economics 3. Those are the 3 different economics books. And then accounting, it's 4. 1, 2, 3, 4. And then it's business studies. For business studies, we have 6. So we're going to create 6 spaces here. 1, 2, 3, 4, 5, 6. So this is accounting A1, A2, A3, A4. This is business studies B1, B2, B3, B4, B5, and B6. So we have now grouped these books for each specific subject. Now remember, we treat this as one object. We treat this as one object. We treat this as one object. So we have 3 groups. We have 3 groups, 1, 2, 3. And then we want to arrange. We can arrange these groups. We can start with the economics books, then accounting books, then business books. Or we can interchange and start with accounting, business, and economics. Or we can interchange their positions. So which means that that interchange can be done in 3 factorial ways because we have the 3 groups. So this 3 factorial is for the groups. We have the 3 groups. Now, if you check within the economics books, we have 3 different economics books, so they can interchange position. E1 can start, or even E2 can start, so they can interchange positions. Since there are 3, they can do that in 3 factorial ways. We are talking to now the economics books. The economics books. Now, if we move on, we have the accounting books. Obviously, because there are 4, they can also interchange positions in 4 factorial ways. This speaks to now the accounting books. It speaks to the accounting books. Now, we also have our business studies books. They are 6 of them, so which means that they can arrange themselves in 6 factorial ways. So we are speaking to business studies. We are speaking to business studies in this case. Now, if you multiply the 3, this would be 3 factorial times 3 factorial times 4 factorial times 6 factorial. So this would simplify to the total arrangement would be 6222080 ways. These are the total number of ways when you say the books of each particular subject must stand together. So they can do that in 6222080 ways. Now, if you move on to the last question, it says accounting books must stand together and business studies books must stand together. So we are only limiting our constraints to accounting as well as business studies. So we're going to group the accounting books. They are 4, 1, 2, 3, 4, A1, A2, A3, A4. This was B. Now we are working with C. And then we group accounting as well as business studies because they said Accounting books and business studies books must stand together. So we have our business studies books. There are 6. 1, 2, 3, 4, 5, 6. Business 1, 2, 3, 4, 5, 6. Remember, we still have the economics books, E1, E2, and E3. Remember, they are not grouped, these ones. They are not grouped because it's only accounting books and business studies books that must stand together. So we treat this one as one object. We treat this one as another object, one object. So we have 1, 2 objects, and then 3, 4, 5 objects to arrange. Remember, now we are not grouping the economics books because they are not part of the restriction that is written in the question, because the question says accounting books must stand together and business studies books must stand together. So those are the books that we're going to group. We leave the economics books as isolated books. So if you want to arrange the first group for accounting, the second group with a business studies, and then you would have economics 1, economics 2, economics 3. So you'll have 5 objects to arrange. In this case, the total arrangement would be 5 factorial for the overall arrangement. But if you look or zoom into the accounting books, they can interchange positions in 4 factorial ways. And then the business studies books can interchange positions in 6 factorial ways. Now, if you simplify that using a calculator, 5 factorial times 4 factorial times 6 factorial. So this would give you 2,073,600 ways. So that is basically how you can arrange these books. I hope that you are getting to understand the trend. How do we work with groups? We treat them as single objects. I'm sure you are getting the drill of things now. Right, we move on to the last part of today's lesson. We are now dealing with arrangement of weights, word arrangement. We are now zooming into word arrangements now. That would be the last part of today's lesson. How many ways can letters of the word problems be arranged? We are dealing with these letters. And then the first letter must be a P. So now, if the first letter is a P, remember we have 1, 2, 3, 4, 5, 6, 7, 8 letters. We have 8 letters here to arrange. 3, 6, 8. Yes, we have 8 letters to arrange. And then they tell you that the first letter must be a P. So what would be the total arrangement? If the first letter is a P here, the first letter here is a P. So what are you doing to this P? You fix it in that position because it is specified. The position is specified. It must be the first letter. So you're going to fix it in that position. If you fix the letter P in that position, you would see that you are left with what? 7 letters remain. It's 7 letters remain. And now remember, if you remain with 7 letters with P, you cannot do anything with P. It should be in the first position. You can arrange the rest. So how many options do we have of having P in the first position? If you check in the word, we have only 1 P. So there is one way of fixing P in the first position, which means that now the total arrangement will then simplify to total arrangement would be 1 times the 7 remaining letters can arrange themselves in 7 factorial ways. If you put that in a calculator, you get that should be 50, 40 ways. That would be 50, 40 ways. If the first letter must be a P. Now the second problem here. The first letter must be a P and the last letter must be an S. Now, you are interested in the first position and the last position. The first letter must be a P. You need to fix P in that position. The last letter must be an S. You need to fix the letter S in that position because they are their positions are specified. If the position is specified, then you need to ensure that you fix that particular object in that position. Now, how many letter P's do we have? It's one option of fixing P there, and it's one option of fixing S there. Now, if you do that, how many letters remain? You've used P and you've used S. Out of 8 letters, you've used 2. So you are left with 6 letters. 6 letters remain. So if 6 letters remain, obviously the P and the S cannot be arranged. They are fixed in those specific positions. So you can only arrange the remaining letters. So the total arrangement in this case would be 1 times 6 factorial ways of arranging the remaining letters there times 1 for the letter S. So that's 6 factorial in the calculator. That gives us 720 ways. So that is basically how you can arrange these letters. That's how you can arrange them if you start with letter P and letter S. Letter P and S are fixed in those positions. They cannot move. You can move the rest of the letters within that specific arrangement. Right, moving on. This example continues. It continues, it does not end there. The first letter must be a vowel. The first letter must be a vowel. So if the first letter must be a vowel, then if we zoom into this, the first position must be a vowel. So we need to define a new subset for the first position. Our subset for the first position is a vowel. Which ones are our vowels in these 8 letters? It's O and E. So we have a vowel O and a vowel E. So if they say the first letter must be a vowel, so how many options do we have of having a vowel as the first letter? It's 2 options because it can either be an O or an E. So we have the remaining letters. If you've used, obviously, you've used 1 letter there. So you are left with 7 letters. If the first letter is a vowel, you are left with 7 letters, which means that the total arrangement for D would be given by 2 times. The 7 letters that are left there, they can be arranged in 7 factorial ways. That is if the first letter is a vowel. So that is 2 times 7 factorial. That gives us 10080. That is example number 10. That is example number 10. 10080. Now, the first and last letters must be vowels. Now, if we zoom into this one, let's do E here. If the first letter and the last letter are vowels, obviously we have 2 options, O and E, that defines our vowels. The subset O and E defines our vowels. The first and last letter must be vowels. Now, if the first letter is a vowel, how many options do we have? We have 2 options. If the last letter must be a vowel, now that you've used a vowel in the first position, you've used a vowel in this position, you now have 1 less vowel. So here you would have 1. Because if you've used an O here, then you will be left with only an E in the last position. So now, how many letters are left to arrange? First and last letters, we've dealt with them. How many letters are left? We've arranged. We've put 1 letter in the first position, a vowel, and we've put a vowel in the last position. So we have used 2 letters. We have 6 letters remaining. 6 letters remain. So the total arrangement in this case would be given by 2 times 6 factorial times 1. So that would be for E, 2 times 6 factorial times 1. So that would be 2 times 6 factorial times 1. So that would give us 1440 ways. That would give us 1440 ways if the first and last letters must be vowels. If the first and last letters must be vowels. Right. And then the last one now, F. The last one now, F. F wants of us to arrange R, E, and S must be grouped together in any order. Letters R, E, and S must be grouped together. So if you group them R, E, S, if you group the three letters R, E, and S, now that you have a group, you need to treat that as a single object, because they must always move as a group R, E, and S. And then how many are left? We've used 3, so we are left with 5 letters. 5 letters remain. We are remaining with 5 letters now that we've arranged, or that we've grouped R, E, and S. Now, if you check the total number of objects that we have, remember R, E, and S can move positions. If the question said R, E, and S must be the first 3 letters, you were going to fix their position. You were going to make sure that you fix the position of R, E, and S. But in this case, they did not say they are the first 3 letters. They just said they must be grouped together in any order, which means they can move within an arrangement. So the total arrangement here, you have the 5 remaining letters plus that group. So it's 6 items to arrange. So we can arrange them in 6 factorial ways. However, the letters R, E, and S must be in any order, which means they can also interchange positions. So we can do that in 3 factorial ways. Remember, if the word any order was not there, if they just said the letters R, E, and S must stand together in that order, it means that they cannot interchange positions. But they said in any order, which means R, E, and S can interchange positions. That can be done in 6 factorial ways times 3 factorial ways. That should be 4, 3, 2, 0 ways. That would be 4, 3, 2, 0 ways. Right. Moving right along. We are now on activity 4. This should be the last activity that you guys should do. It should be the last activity that you guys should do. And we are running out of time, so I'm only going to give you 2 minutes to work with that. You have 2 minutes to work with activity 4. 2 minutes. Right, hello and welcome back. We said this is the last activity. What I would ask of you is you can take a picture of this specific problem so that you work it out on your own, because the time that I gave you was not enough. You can work it out on your own, but then you fortunately will have the solutions at your disposal because I'm about to work out the solutions with you. Right, how many ways can letters of the word decimal be arranged if the letters may be repeated? What I tried to do is I have my solutions this side. How many ways can letters of the word decimal be arranged if letters may be repeated? We have 1, 2, 3, 4, 5, 6, 7. We have 7 letters. So if you can repeat the letters, the first one, if the letters may be repeated, our total arrangement would be, remember we have 7 letters, 1, 2, 3, 4, 5, 6, 7. So for the first position, we will have 7 options. For the second position, we'll still have 7 options because remember, they are saying letters can be repeated, which means if you started with D, you can use a D again. So for the third one, it's still 7 options, 7 options, 7 options, 7 options, 7 options, because you can actually repeat, or you can use the letter more than once. So this is the same as 7 exponent 7. So if you have that as 7 exponent 7, obviously we are saying it's 7 exponent 7 because letters may be repeated. That would simplify to 8, 2, 3, 5, 4, 3 ways. That is the number of ways in which these letters can be arranged if the used letter can be repeated. However, if the repeated letters, if the letters may not be repeated, or rather in B, we are saying letters may not be repeated. So the total arrangement in this case would just be 7 factorial, because you'd have 7 for the first position, minus 1, 6 for the second position, 3, 4, 5 for the third, 4, 3, 2, 1. So that is 7 factorial if the letters may not be repeated. So that is 50, 40 ways. Now, the third question is the arrangement must start with a vowel. We need to start with a vowel and end in a consonant, and no repetition of letters is allowed. So we start with a vowel and we end with a consonant. So this is at the start and this is at the end. We end with a consonant. So we are going to define our subsets. We are going to define subsets for vowels at the beginning. Obviously, the vowels that we have here is E, I, and A. So A, E, and I, those are the vowels. The consonants becomes those that remain. So we have that as D, C, M, and L. Those are our consonants. So we've defined a subset for vowels in the first position. We've defined a subset for consonants in the last position. So how many options do we have of starting with a vowel? It's 3 options because there are 3 vowels. How many options do we have of ending with a consonant? It's 4 options because there are 4 consonants. So now there are those that are going to remain. We've used 1. Obviously, we have 3 options for the vowels, but we'll use 1. We have 4 options for the consonant, but we'll use 1 as well. So how many letters are left? We've used 2 letters, 1 at the beginning and 1 at the end. So we are left with 5 letters. So to arrange these letters, the total arrangement would be 3 times the 5 letters that we have remaining there to arrange. We can arrange them in 5 factorial ways because they can interchange positions. And then the last one, obviously, it's for the consonant. So this is 3 times 5 factorial times 4. This simplifies to 1,440 ways. That is for C. The arrangement must start with a vowel and end in a consonant, and no repetition of digits. What we did was we defined a subset for vowels and we defined a subset for consonants at the beginning and the end respectively. We said we have 3 vowels, 3 options. We have 4 consonants, 4 options. the 5 remaining letters, we can arrange them in 5 factorial ways. Right. Moving on to the last two, D and E. The arrangement must start in a consonant and alternate between vowels and consonants. No repetition is allowed. So this arrangement for D, going to put it here. This arrangement for D must start with a vowel, and then it must alternate between, it must start with a consonant and alternate between vowels and consonants. Now this would be 1, 2, 3, 4, 5, 6, 7. Start with a consonant, vowel, consonant, vowel, consonant, vowel, consonant. It starts with a consonant and alternate between vowels and consonants. Now, let us look at the arrangement only for consonants. How many options do we have of starting with a consonant? It's 4 because we had 4 consonants. How many options do we have of occupying the third position, which is the second consonant? It would be 3 options. 2 options and 1 option. Remember, I'm only looking at my consonants for now. I'm only looking at my consonants for now. If I start with a consonant, I have 4 options. Then moving on, the second one should be a vowel, I leave it. The third one should be a consonant. I've used 1 consonant already, which means I'll have 3 consonants. On the 5th position, same thing. On the last position, same thing. Now with the vowels, we said we had 3 vowels. So to start with a vowel, there are 3 options. And then if I've used 1, there will be 2 options here. If I've used 1, there would be 1 option there. If I multiply all of them together, this arrangement will simplify to, for consonants, it would be 4 factorial. For vowels, it would be 3 factorial. That is, if you look at that and you try to congest it using the factorial notation. So that would be 4 factorial times 3 factorial. That would simplify to 144 ways. That is the number of ways that you can have vowels and consonants in alternate positions, starting with a consonant. Now, letters D, E, and C must be the first 3 letters. Now, this is very, very important. Must be the first 3 letters. Now, if you check, we've worked with one here which said letters R, E, and S must be grouped together in any order. It's different from the one that we are working with now. This one says letters R, D, E, and C must be the first 3 letters, which means you group them, D, E, and C, and then you're going to fix their position because it is specified that they must be the first 3 letters. Now, they said in any order, which means they can interchange positions in any order. If they said D, E, and C must be the first 3 letters in that order, then they cannot interchange positions because the order is also specified. In this case, the order is not specified. They said in any order, but they must be the first 3 letters. Now, if you have D, E, and C being the first 3 letters, how many letters are left? We have 4 letters remaining. 4 letters remain because we have 7 letters in total. We have 7 letters in total, so we have 4 letters remaining. So the total arrangement, remember this, I'm not grouping it. I am grouping, but I'm not moving this. I'm not treating it as a single object that can be moved. It cannot be moved. This group cannot be moved because they said first 3 letters. So it was specified that they should be the first 3 letters. So I'm not going to arrange these 3. This group in the group, I'm not going to arrange the whole group. I'm going to arrange the 4 remaining letters. I can do that in 4 factorial ways. Multiplied by, within the arrangement D, E, and C, I can interchange them. They can interchange positions because they said in any order. They can interchange positions in 3 factorial ways. That is also 144 ways. That is also 144 ways. That is basically how you work with D and E. Right. Learners, we are done with today's part of the counting principle. We've come to the end of today's lesson. I am urging you to connect next week when we look at the second part of the counting principle, part 2, where we'll be working with digit codes and the rest of the things that are remaining in counting principle, as well as applying our knowledge of counting principle to solve probability problems. So we've come to the end of today's lesson. Please remember to practice mathematics all the time as you prepare for the prelim exam. Please set your own targets and work on those targets so that come prelim examination, you are able to get the marks that you deserve to get. For now, it's bye-bye. Take care of yourselves and take care of each other. Bye-bye. See you next time.